So today is actually the finale of the GT Neuro Seminar Series for this year. As you guys know, that this seminar series kind of encompasses celebration of neuroscience and neurotechnology, and I actually can't think of a speaker who better kind of encompasses this celebration on a global scale. Michelle Johnson is our speaker today. Her career has spanned, I think, 4 different continents. So she got her training in her BS in mechanical engineering and applied math from the University of Pennsylvania, her MS in mechanical engineering from UC Irvine, and her PhD in mechanical engineering from Stanford, where she focused on mechatronics, robotics, and design. She did a brief postdoc at the Advanced Robotics Technology and Systems Laboratory at, I think it's Scuola Superiore Sant'Anna in Italy, through a fellowship from NSF and NATO. In her independent career, she's established a research program that focuses on the use of robotic technology in order to aid rehabilitation and to improve quality of life for individuals living with neural injury. She started at, I believe, the Medical College of Wisconsin and Marquette University in Milwaukee, and since 2013 has been at the University of Pennsylvania, where she directs the Rehabilitation Robotic Research and Design Laboratory. So her lab has made a number of really important advances in a number of different fields, including upper limb rehabilitation for individuals following stroke or brain injury using robot-mediated therapies. And I actually heard of Dr. Johnson's work when I was a grad student and feeling really pulled between kind of this high-tech neuroprosthetics work and also just simple interventions for practical implementation in medically underserved communities. And for those trainees who are out there kind of feeling the same way, I think that Dr. Johnson's research is really evidence that there's a lot of synergy between both of those things. So she develops intelligent robotic systems for neurorehabilitation with an emphasis on affordability and implementation in low-resource communities. And these technologies have improved both quality of living for patients as well as yielded new insights about plasticity during rehabilitation from cognitive and motor impairment. She's implemented these technologies in communities across Latin America and Africa, and actually right now she's a Fulbright scholar in Botswana, but has made a nice detour to come visit us here to give a talk. So with that, I'm very happy to introduce Michelle Johnson.
Thank you so much. Thank you, everyone. It is my pleasure to come and visit Georgia Tech. I've been here right before the pandemic in 2019. Gosh, it's been like a long time. Feels like decades instead of like a couple of years. Anyway, so my talk today, so I just actually came back from Botswana. I was there for 2 months, and on like the last leg of my my Fulbright scholarship. And so I decided, okay, I'm going to bundle that and kind of talk a little bit about kind of my journey a bit, and then kind of what are some of our findings that we're just getting out of our Botswana work. Let me start, this didn't move. Couple of quick financial disclosures. I have to say this because there's a spin-off company out of Penn called Recupera Robotics that's kind of spinning off some of the affordable robots work that we've been doing. So the area of kind of thinking about therapy and assistive robots, you guys are probably already familiar with. So I've been working mainly with kind of thinking about therapy robots, which I define as robots that are specifically trying to assist recovery after neurological function in my case, and assistive in the sense of robots that's trying to replace or help support the acquisition of functional activities. So one of the things that my lab does is we work really closely with MDs and clinicians, and we try to study kind of what's actually happening in the clinical area. And there's a work that we're actually currently about to publish in IJSR, where we're observe that kind of the therapist and the patient is kind of in this kind of dyadic space, and where we see that the robots are functioning as demonstrators while the patient's observing. There's actually 3 groupings that are happening. Therapists observing while the patient's doing, and then the therapist helping while the patient's performing. So even in this kind of setting of a stroke rehabilitation setting, we see 3 general uses for our robotic systems. So if we're thinking about, as I think about robots as therapists or robots as assisting therapists, I'm thinking of them as helping robots. So that's kind of our classic therapy robots, demonstrating and observing, and these are our classic assistive robots. And we actually don't have a lot of robots that do it all, right? That do both the fluid transition from holding on to someone and helping them, and then observing them, monitoring as the human does. So at the beginning of my work, I kind of spent a lot of time in thinking about motor recovery in the real world, in how we can use robots to support the upper extremity for real world tasks like drinking, feeding, and this is one of our first systems that we had put together called the Adler system. And then we kind of more recently, I've done a lot more with what I call assistive robots, thinking about making demonstrator observer robots. This is a system that is built by my current PhD student, who is actually a week from defending his thesis. And this idea of this system kind of being a demonstrator system, it's non-contact, and being able to help remotely adults and patients. And then we also kind of work on the classic humanoid that might be more demonstrator observer again, and a cooperative, collaborative player with the patient. This is my colleague, Dr. Kuchenbecker, who I was co-advising a student of hers, kind of thinking about humanoid robots at play. Of course, this has been now kind of a pretty, I remember when I started I date myself, but the 90s or so, kind of thinking through these issues. And now there's like a lot of data that's kind of telling us these robots are actually doing something. So we know from the body impairment, body structure, we know it's increasing strength, increasing motor control, reducing spasticity, all these really good things that we can actually quantify now. From an activity space, we see that, yes, when they're task specific, we see return of reaching, return of grasping. We also see improvement in activities daily living, but that's always remained inconsistent. This has been a challenge. And this actually, and then we also see more in participation with exoskeletons kind of moving us into community-based place. But a lot of times they're also not relevant to low resource settings. The challenge of cost and of those types of issues make participation for the wide variety of the world very difficult, right? So this kind of, brings us to kind of thinking about, well, there's some really great things that we're doing with robotics, and then there's some things that we need to consider. And how do we challenge them? So the list you guys probably know, it's repeatable, it's adaptable, can help us with semi-autonomous training. We can get consistent force application. There's some we can get some great reps out. However, they tend to have challenge with transfer of recovery to real world type tasks, high cost for the most part for most of the communities that are kind of out there that's struggling with neurological impairment. They can be super mechanically complex, which is not a bad thing all the time, but it might also, there might be a relationship between mechanical complexity and cost. And then they are often quite huge, and they're often very targeted in one way. And so many of the real world settings that are out there can't kind of really deal with these types of systems. So they're not quite accessible then to community-based settings, to skilled nursing facilities, to places in the global spaces that I've also been working in. So when we take a look and we step back and we say, where are these robots actually globally? We see that they're primarily in high income spaces. So a lot of the data that we've gotten on the goodness of these systems and their effectiveness in terms of neuroplasticity, driving that, enabling, recovery for many people with neurological impairments, a lot of the data is coming from high income spaces. And so my push has been, how do we take what we've learned from these complicated systems and how do we map that into maybe lower degree of freedom systems, but also mapping it into low resource status within the United States in community settings, as well as in the global space and global settings. I like this map because it was 2014, I put this together when I was starting to say, the difference between high income spaces and global, am I standing in your way? High income spaces and low and middle income settings when we think about the prevalence of the diseases that we care about, cardiovascular, cancer, diabetes, communicable diseases. We see that the higher income spaces, we see that they're going to be more likely have higher percentage of cardiovascular issues, lower issues with infectious diseases. This was 2014. COVID has kind of changed it a little. I know, so I'm always presenting data now pre-COVID because COVID just totally threw everybody off, right? And then what we see in places, for example, like Botswana, we do see this area is now growing. Lot more communicable diseases happening, lot more non-communicable diseases like diabetes, hypertension, and then the infectious disease rate is going down, but it's still pretty high. So these communities are now dealing with kind of this dual issue, right? And so this becomes quite challenging. But the challenge is that they need these robots just like we do. So what are the challenges, though, when we push more in low resource settings? And I will say low resource settings because it's not just about developing countries. It's about the urban site, the skilled nursing facility that's down the street from Penn, right? So it's about those sites as well. Is oftentimes so in just thinking about developing countries, the issue is also disease focus. We're more focused on the disease and less on how do you live after disease. And because of low resources, the country structure might be challenging for implementing these types of robot systems. But rehab access is low, so that actually creates an opportunity for the technology, and that the skilled therapists and physiatrists are often not available in Botswana. There are 0 physiatrists. Physiatrists are rehab medicine docs. Super important for that rehab quality of life. There's 0 physiatrists in the country. Low doctor-patient ratio, low patient-therapist ratios. The rehab technology, if it's there, it doesn't kind of exist in the quantities. And we actually recently did a survey. One of my goals was to survey what's going on with rehab in Botswana. One of the things we found is that, for example, the World Health Organization, I don't know if you guys know this, came out with a 50 list of the most important assistive technology that should be in a country. And Botswana is one of the countries that signed up on that, saying we're going to dedicate to make sure that people with disabilities have access to these 50 technologies. Most of them are like, for example, rollators, walkers, canes, simple things. When we queried people in Botswana, like most of these things don't exist, and if they exist, because there's no local manufacturing for rehab, everything is imported, and now we're quadrupling the cost. A simple cane now costs a whole lot more money than they can afford, and a wheelchair, once you import it, it breaks. No one fixes it, and so therefore it's more expensive. So there's these really weird dynamics. So now let's fast forward to robotics, and people are like, wait, there's an oxymoron here. Robotics and developing countries, maybe that not so smart. But I push back and I go, but these are the spaces that might need us to really think about this even more. Because one, they're fascinating, the type of interplay of disease that's happening there, but then also the issues of access is very startling. Here's just a quick statistics. You can kind of high-income countries, the ratio of doctors, medical doctors per million population. Here we are in some of the areas that we consider low and middle income, they're struggling with down to very close to the zeros. Here, when we think about the density of physiotherapists, which is often, if you say we're the therapist, most of the time you encounter a therapist, they're a physiotherapist. There are not as many specialized therapists like speech and language or occupational therapists. They're broadly, for the most part, mostly physiotherapists. And the luxury of having therapists that fully specialize is not there because there are not enough of them, so the therapist has to do a lot of different things. You can see this, the disparity between the number of therapists available and what's happening, example, in the Africa region. So I always have this nice slide, and I always think of the gap. The gap is huge in the developing world, but the gap exists also in the US. And that's what I don't forget that, because I see this gap also in the community as well. So we assume that technology can help bridge this gap. But one of the challenges with technology is how can we make them more inclusive and how can we make them more affordable? I use this definition, affordability being the extent to which something is affordable as measured by its cost relative to the amount the purchaser can buy, right? So when we think about what is affordable, I use the World Health Organization guideline, which is really actually kind of cool because they say, they actually came up with something that's economically can be appreciated, and it's based on the gross domestic product per capita. And so what they argue is that if you can make something and you implement a technology that is within 1 GDP, then you're going to be highly cost effective. And this is talking about cost and benefit ratios. If you can focus that, okay, it will be it's less than 1 GDP per capita, highly cost effective. If it can be between 1 GDP and 3 times the GDP per capita, it's cost effective. And then something that's beyond that is unreasonable. So I took this and I said, well, could we loosely use that as a kind of a cue for how we implement technology? And if our robots or our systems or technology systems can fit these criteria, maybe then they begin to be affordable, right? Just begin. I say that facetiously because with the dollar and the differences in economics, it becomes hard to even say that. So, for example, the U.S. GDP per capita is said to be 53,000. Of course, we know there are people that make much more money than that, and people make a lot less money than that. So just bear with me that this is pseudly the average. And then the 3 times that is 159. So when we buy rehab robots that cost 250,000 or 150,000 or 100,000, most hospital systems are not blinking. They're like, okay, that's okay, but the community centers are like, we can't afford that. We're more like operating on the low middle income space. And when we think of Ghana is 7, this was, I think they're increased right now to maybe about 10, but there's still a significant difference in what is considered cost effective. So when we were developing systems, we wanted that the entire system would be under that number or between these 2 numbers, right? So those are the numbers that we're working with. I find that this is actually effective in kind of making me put cost within my infrastructure of design. Some of my colleagues will say, no, we want to make the best robot system possible, no matter the cost. We want to deal with the science first, and then we deal with the cost. I agree on some level, but I just realized that designing and putting cost as a constraint on my design and the effectiveness of my intervention forces a sensitivity within me that actually pays off in the end. I know not all my colleagues will agree, but I think that if we actually design and push with cost in mind, we might even innovate even more as a result. But this is my opinion, right? You brought me here to give you my opinion. So I'm giving you that. So we actually had a colleague in Italy working on kind of doing a review on affordable robots out there, what's going on. And there are people working in this space and trying to push that envelope. They said, this is our system, and we're one of the few people that have actually trying to put our money where our mouth is and do this type of work. But I'm happy to see colleagues like starting to push in that direction as well. The potential strategies that you see out there, that when we looked at the literature, using low-cost robotics, mechatronic systems, not being committed to the 6 degree or 7 degree of freedom systems if possible. But if they are going to have multiple degree of freedom, kind of thinking about cheaper materials, soft materials, 3D printing, those types of things, we see that as a way people are doing that. Also using a system of low cost or low degree of freedom and using those in creative ways, as in 1 degree of freedom system, could it be modular? Could it build to a 2 degree of freedom system? Or could a 1 degree of freedom system itself be just oriented manually or rearranged? Or you challenge it by putting 2 1 degree of freedom systems together. So these are kinds of strategies that I see people doing in order to try to push this envelope of an affordable system. So one of the big things that I realize is this idea of using local manufacturing and resources. So in sense, this is actually me coming to this conclusion after spending time in Botswana, realizing that I can price something at $5,000 US dollars. That is it's 11 pula, which is the dollar in Botswana, to $1 US dollar. So all of a sudden, my 5,000 system becomes 50,000 pula, and they're like, we can't afford that. And then I have to go, okay, this is interesting. So I've learned very quickly that collaboration is key, because using local manufacturing and resources can drive that cost to now where it's affordable. So we built a memorandum of understanding with the University of Botswana so that I could share the tech in my lab with the university there. And then what we were able to do was build a lot in-house that then was able to drive down the cost of the system that we're using there. So just an interesting strategy. This challenge, though, economically, I'm not an economics, but some people might say, is that sustainable or not? But maybe I need to find some folks who I can collaborate with to answer that question. The practice, inclusivity, practice of providing equal access and opportunities and resources for people who might otherwise be excluded or marginalized as those that have physical or mental disability or belong into other minority community. Sometimes people go, why are you using that term inclusivity? And I said, I guess it's the, thinking that my passion for being in the space of working with people with disability was always about making sure that no one felt excluded, right? Making sure that if you had an impairment, that you had the hope of getting back, right? I know it's not always the case for everyone, but they had the hope of getting back to yourself. And it began with my grandmother. And if anyone have ever seen my TED Talk, my grandmother's why I'm here. Because when she had a stroke and I saw how it took her from this dynamic woman to someone who was wheelchair bound, I became committed to figuring out how we can change this dynamic, right? Yes.
I just wanted to say we have a question from the online audience.
Oh, sure.
This is from Steve Wolf. He says, also, this is a question about the cost part. Cost includes the time for the clinician-family interface. What is the evidence between cost of robotics and their efficacy or effectiveness in securing a given functional outcome? And is that interface superior to one-on-one treatment or interfaces?
Okay. So there is some evidence. So a lot of the evidence around robotics have been mixed in the sense that there is a clear sense that it may not be better than what's happening with the physiotherapist. That if you dial in intensity and you dial up intensity and you dial up and you match dosage, that what the therapist can deliver is equal to oftentimes to what the robot can deliver. But I don't view that as a bad thing, because in these spaces there are no therapists, and therefore that's why I push that the opportunity for robotics is higher in these spaces where there is no therapist. We can have that argument in America where there are a number of therapists, and so we argue robots shouldn't be replacing therapists. That's not about what I do. I bring in intelligent robotic systems to work alongside therapists. And that in that evidence, we maximize the therapist's ability to do more. But where I drive the argument that robotics become a superior possibility is when there is no therapist. And that's the only way that people are even going to get access. So I push back on that and say the evidence is the fact that it can be pari gives us the opportunity to now explore whether it can be a vehicle through which we can manage these access issues. So, but that I think is research that people like myself are trying to do within these spaces. Hopefully that answers the question. So one of the things of inclusivity that we were thinking about was oftentimes in rehab, even as engineers often, or when we start to do experiments, we try to control the problem and we look at disease as having one effect. So most of the time in robotics, when we began, we started just thinking about motor issues. People with motor function, stroke survivors have primarily motor function, but the reality is stroke survivors have a plethora of issues. And that oftentimes cognition is a major part of that. And the fact that most often there is actually some really good research that shows, 77% might have upper limb impairment, but 43.9% are dealing with cognitive impairment, mild and sometimes even severe. So the question then becomes, how could we move and be able to use Robot One with a larger community? That my clinical colleagues push that to me, saying, hey, these robot systems are often not really included these other population, these stroke survivors that have cognitive issues. How can we change that, right? The second thing was thinking of that because cognitive function is not commonly used. When we looked at the literature, we looked at all the robotic systems over there. Most of them, and most of the studies have done with people with mild to no cognitive issues. So there's an assumption that the people doing and using our robotic systems don't have any cognitive issues, and therefore the recovery that we're seeing is possibly challenged by that naive assumption. Because when someone gets recovery and they go out into their regular environment, the cognitive demand of doing motor tasks as well as the cognitive demand of living and doing motor function begins to challenge their ability to transfer what they learned to the real world. This was my theory. And we began to say, how can we look at that and examine whether that has any truth? We also kind of said, well, if we took a simplistic approach and we said the x-axis is our motor impairment, high impairment here means low function, low impairment means higher function, and then the y-axis is our cog axis, and high impairment means low cog function, and low impairment means high cog function. So I say that because I may use the term interchangeably. What we see when we look at the robotics landscape, when you look at like this quadrant, these were kind of people who were already kind of, mild stroke, almost fully recovered. Most of what we do in robotics is this group. Low cognitive impairment, high, moderate to high motor impairment. Here, lack of effective measures. Most people exclude this population. And then this population often have only cog rehab and not any motor rehab. So we realized that there was an opportunity here to really think through how we can include more within the concept of our robotic assisted therapy strategies. This is why we started looking at motor and cog together. So that plus our typical design goals kind of led us to start really rethinking. I'm going to talk about two case studies really quickly. One is the work that we did in Mexico that kind of gave rise to what we call our rehab cares system that we've deployed in Botswana. And then two, I'll talk a little bit about the work that my PhD student in terms of this issue of looking at motor and cog together and how it influences kind of how it might influence recovery after motor impairment, how we might be able to possibly use this to determine how robotic systems could possibly function in the future, but even how we can use it to understand what might be going on after HIV and stroke. So this work in Mexico was kind of done a little bit towards my time in Wisconsin. I was working with this colleague who was in Chihuahua. She was a bioengineer professor there, and we collaborated together to look at this idea of just my preliminary work of getting affordable mechatronic systems out there. So we worked with specific stroke. Most of you are probably already familiar. So a couple of different ways that you can get ischemic stroke, hemorrhagic. Ischemic stroke is by far the most popular, especially in developed world. Hemorrhagic stroke tend to be higher in the developing world. 800 strokes per year in the U.S. costs a lot of money, so there is reason why we're all thinking about stroke recovery. And stroke survivors have, depending on the quality of rehab, even in the United States, may not be getting enough therapy in order to make a difference in terms of their recovery. So this is the typical kind of characterization of, the severe person with severe stroke having the upper extremity and then having mobility issues. This talk will be more focused on the upper extremity. So, truth, 46 to 61% of stroke survivors will have cognitive impairment, which is why we feel like this is the direction that we really need to think as a field. 65% motor. They'll also have psych issues as well as impairments in their living and activity of daily living. This is why even considering this space here says the individuality of the stroke survivor and why it's important to figure out where they are on the spectrum. In our case, we're looking cog and motor, and then determine how do we then treat this person given that spectrum. Initially in Mexico, I started working with, can we just not use robotics and just use simple like force feedback haptic systems? That was my first question. And then, and so in Mexico, we developed we were using force feedback wheels. And so we were putting gaming together. We were one of probably the first labs to start thinking about can we just have people play games and those have, helpful consequence. One of the things we got a grant, my colleague got a grant from Mexico, and then I had some funding to put together kind of what we call a robot gym. And it's basically a computerized mechatronic gym with 6 stations. And then we published this work, and we basically randomized people to going to regular therapy and going through the gym for upper and lower limb therapy, because we wanted to be comprehensive if we were going to prevent people from doing the standard of care. We also kind of looked at 20 stroke survivors, and we examined, they had a variety of different strokes, various levels of function, control group, robot group. What we discovered, and I don't know if I kept it in the slides, but we discovered that they were able to recover both on the upper limb and the lower limb. The lower limb did better than the upper limb. And then that we also saw that the robot gym had 2 really great unintended consequences. Working out in a group was fun. And people were like, hey, can I keep coming back? And we were like, okay, this is an unexpected, plus. And then 2, the time and the energy to both play games and work out, really people felt like, hey, I am getting my exercise in and I am getting better, but I'm also doing it in a way that was enjoyable. Not to say that they didn't enjoy working with their therapist. They actually did enjoy those one-on-one interactions, but this became kind of, a really interesting thing. One of the things we found out, though, was the force feedback wheels were inadequate. they were not powerful enough for very severe stroke survivors. We needed to be able to assist them when they couldn't move. So the robot needs to be able to be strong enough to apply torque, if it's going to be a 1 degree of freedom, to help move the system. And it couldn't do that for the very severe functioning patients. So we went back to the drawing board and started, okay, can we develop a 1 degree of freedom system, still thinking about low cost, that would help us to work with both the severe, the moderate, and the mild functioning stroke survivors. So hence, that led to kind of this simple robot system here. There is 4 sensors in the handle. There are position encoder, very simple system. And we basically can do adaptive strategies to assist when needed and to resist if you're doing really well in terms of performance. We could then do like an anti-spring or challenge you in some interesting way. We also realized on the gym idea that maybe we shouldn't be thinking about just one isolated system off in the corner, but can we, in the idea of working with the upper limb, the lower limb, having the arm working different ways, because these were 1 degree of freedom systems, we could populate them around a structure that would allow us to maybe now have multiple people working together in a gym. Why did we create this structure? So this was our first prototype of this platform, and then we decided then, okay, this platform, if we build it where the center part was a gate platform, in places where they have a gate platform but no space, we would replace the gate platform with our robot system. They'd still have a gate platform, but now they would have a couple of robots in the system. We also talked about how do we do, I have a PhD student right now looking at haptic dyads. So basically, if a stroke survivor is working with a 1 degree of freedom robot and another is working with another, how do we have them interact? Where now and how does that interaction increase the motivation, increase maybe the challenge, maybe increase on drive to plasticity? That she's at the early phase of us looking at that. Turns out there's a lot of work where people work with healthy subjects doing that, but not a lot of work where people work with impaired subjects in that paradigm. So the work in Botswana then, my PhD student, we started asking the question, how does cognitive issues affect motor performance? That was kind of a fundamental question that we wanted to answer. And why we did HIV, most people go, HIV, what does that have to do with stroke? But there is a long story as to why I'm in Botswana, but the bottom line is HIV is a risk factor for stroke. I had a colleague working in Botswana who was telling me that 1/3 of the stroke survivors had HIV, and that oftentimes the first time someone comes to the hospital with a stroke, they don't realize they have HIV, and that could have been the reason for the early stroke. And that later on, there's a knowledge that the HIV leads to a type of stroke that's different from the average stroke that you get when you have comorbidities, et cetera. So it was actually a really fascinating place at the time. So now with antiretroviral, yes?
Can HIV also lead to like weight loss and atrophy, which will then affect the muscular system, which will increase the need for?
Yes. And what's interesting too is we started working with Botswana because it was one of the first countries where antiretroviral therapy was in place. But so many of the people in Botswana are on ARTs, but we were still noticing neurological disorders. We're still noticing what they call HIV-associated neurological disorder or HAND, and that there was a significant percentage of the population that might be actually having these cognition and motor issues. So the other issue is the HIV population, they're living, they're surviving. Now they're becoming chronic over the age of 50, and now stroke is just the regular stroke is starting to catch up with them, with the comorbidities, hypertension, et cetera. So how do we deal with the complications of stroke was what was put to me, and whether our robotic systems could help one assess and possibly treat. So it was like a good way to think about how do we translate our stroke work into HIV, and how do we deal with those with HIV and stroke. So that's kind of where my student spent a lot of his time kind of really thinking about ways we can do this. So long-term impairment, 40% of HIV will end up with some type of neurocognitive disorder. Turns out 70% of them have some type of motor dysfunction. But what's tragic is most people with HIV do not get any rehab because people assume they're okay, right? And so this is actually one of the novel areas that we're pushing it and trying to support the need for rehab and whether robotics can support that population or not. They also then will have difficulty with instrumental daily living, and so it is a population that might benefit from 1, assessment, and 2, therapy. So one of the key things that I had my student do was think about, how do we do this? How do we try to figure out how motor performance is affected by cognition? So HIV became our example group, and stroke as well. So these are 2 populations that we decided to study. So key targets for clinical assessment. There was a lot of work that showed that HIV predominantly affects the prefrontal cortex, and that might be more related to executive functioning, information processing, things like that. So we decided then to put together clinical tools that could kind of look at these particular cognitive areas as well as generalized clinical tools. So I'm going to go pretty fast. So our goal was to develop a robot-based metric that could quantify motor and cog and put someone on a map for us to see where they are. And then if we could stratify them, the next step would be to say, how do we then define an appropriate rehab or robotic strategy that would then help that patient move and recover. So this was the study. This was the first done in the USA. Had 15 HIV, 6 stroke, and then the combined was about 21. The key thing here, he had the MOCA is the Montreal Cognitive Assessment, the International HIV Dementia Scale, and then we also use gross box and block scale. But this was just the comparison. So people with HIV and stroke, and I'll for the time I'm gonna get this and move on. So I had him put together motor assessment from our consultation with clinicians. Everyone did, only stroke survivors did the Fuggemeier, but everyone did the box and block grip strength and the groove pegboard. And then we had cognitive assessment, the Montreal COG, the HIV Dementia Scale, color trails 1 and 2, and digital symbol coding. These are for information processing. Digital color trails 1 and 2 are both visual, spatial, and executive function. International HIV Dementia Scale was essentially said to classify whether you had severe dementia or not. And the Montreal Cognitive Assessment looks at 6 domains of cognition. So we kind of like double think. So if you've never seen the box and block, this is like a really simple measure. It's like a minute on each side, and you're trying to figure out. I don't know. You're trying to figure. You have 1 minute to get as many boxes across. This is supposed to be for gross reaching and grasping motion. Let me. So there's a little bit of delay, but that's okay. This is the group pegboard for those who are not familiar. Essentially, it involves both motor and cog, and it's more fine motor function. You have to put as many pegs in and in as little time as possible. And so the faster you do it, the better your cognitive and motor function is, right? This is the Montreal cognitive assessment. You have to be trained to administer it, but basically it looks at visual, spatial, executive function, naming, memory, attention, language, abstraction, and delayed recall. And this was actually made famous by Donald Trump when he said, it was hard. This was the test that he did. This was the test. So This color trails test is actually like a trail making. It's classic cognitive test that's used. Essentially, if you can count up to 1 to 25, and then essentially there is a process for making and the connection box. This is really a great simple test, but it's really good about looking at executive functioning. So if you need a quick way of looking at executive function, I recommend some of these simple tests. So then robot-based measures, we decided then to develop a robot-based measure that was mostly motor, then one that was mostly cog with the working memory, and then one that required both. So the mostly motor one, this does take some spatial, it has some cog in it, so it's hard to really pull separately, the cog out, but this is mostly motor. They're tracking a task, and they have to keep the green, the robot in the green box. The robot is their icon, and essentially these are the metrics that we pull out: mean performance error, normalized travel distance, things like that. Then this is what you would get depending on what level of function, how well were they able to track the task. Then the cognitive task was the working memory task. 0 back, 1 back, 2 back. 0 back is like no memory involved. Every time you see a 2, press the button. 1 back, every time you see a number repeated, press the button. And then it gets a little harder. Now you have to remember every time you see the number before, 2 back before, press the button. So this wasn't actually, I call it facetiously a robot task, but it was really just a button press. and we looked at correct responses and reaction time. So then this was the task that my student put together from the Sternberg task, which is actually a very common cognitive task that's done. The idea here is the patient is shown a sequence that lights up. This is the cog part. They have to remember the sequence, and then they have to move the robot in the exact order to acquire the box and light it up. So now they have to remember, then move in the order of the sequence, and that was what determined. It was adaptive, so they were first given 3 boxes to light up. If they got it right, yay, they get 4 boxes. If they got it wrong, went back to 3, got it wrong, goes to 2, and it went up and down until we figured out what was the best combination. We did this both with the dominant and the non-dominant limb because the fact of we were trying to look at motor, how does motor performance be affected by cog as well as vice versa. And if the impaired arm was also in charge, we knew that there's going to be a component of the performance that's going to be biased by the impaired arm. So we had them also do it with their less impaired arm or their non-impaired arm in order to see kind of, can we tease these two things out? So this is kind of what you might, the results might look like. People with no impairment tend to be able to remember longer sequences and be able to move well to the sequence. People with motor-only impairment will tend to remember. They'll be a little bit more over to, they'll have less sequence, so the histogram is shifted. Turns out the cog only was overlapping the motor only, and people with motor and cog impairment are the lowest functioning folks. So when you see it, there were 15 trials. You see, everyone has kind of a learning, But if you're not impaired, you see, of course, you see like there's a little bit of a fatigue effect because this is not easy. And if you're not less impaired, you see that you're able to get up to high mean as a trial number, and your sequence length gets pretty high. When you have both, you're actually really struggling, and you don't quite learn as fast about what's happening. And then if you look at the motor only and the cog only group, they're hanging on top of each other, right? And we're like, okay, can we tease that out some more? It's implying that the cog is affecting your motor performance, because if you have high motor function, the cog issues that you have actually warps your ability to perform. And intuitively, that makes sense. It's funny. There was a couple of neurologists on my PhD students team, and they were like, "We know that." So I'm like, "But roboticists don't know that." And it's like, when we're trying to apply these things in the real world, he's like, I said, "But you guys know that, but you never really quantify it in this way that then it allows us to be able to take that information and make use of it." So this was a really big finding. And the other thing was, could we predict the clinical measures of cognitive from the robot task? Now, this is something that was super important for us, because if we could predict with a reasonable strength, then this means that maybe on the fly we could adapt things, right? If we knew and we could personalize the therapy by understanding where you were on this map, and then try to drive accordingly. So here we were able to see that for color trails, a visual spatial tracking, there was a strong relationship for an information coding. This is digital symbol coding. There were two strong relationships that showing that the spatial span, that task that had both, was able to predict your information processing speed with pretty good, reasonable accuracy, and then also your color trails performance, which is your visual spatial performance. We also saw that spatial span task was also able to predict your color trails too, with pretty decent, not as strong as the digital symbol coding, but the R-squared value. And the reason why I put this up here, I'm borrowing slides from my PhD students' work, was this is what we see in the literature, where most people were reporting and using predictive values that were R-squareds in the 0.4, 0.3, and we were able to even get values that exceeded that. And so these were more moderate type results. And then in terms of motor function, that box and block task, we were back up to strong, where what predicted box and block was both the spatial span task as well as that tracking task, your normalized distance. So arguably, what we're hoping then is now, the question then was, could we so we can do both things. We can put people on classify them using the clinical scores. The box and block was translated to a Z-score, 0 being what is normal, and -2 is 2 standard deviations below the mean. That is the beginning of the moderate, the moderate function. And if you're up here, you're mild, right? You're mild. I'll move quickly. You're going to be. This is the high group, right? Remember, and so this is using those clinical scores. But now, if we can predict these clinical scores, we can use the robotic measures to map people. And then if you're up here, this is the people we normally treat. But now, if we know you're here, how can we treat you? What do we do? And it turns out that there are a lot more people here than we realized, right? So we now have the potential to on-the-fly strategy. So my PhD students are working now with what is that on-the-fly strategy? What do we need to do now to deal with people in these different groups? How do we personalize that television? So I'm just quickly going to zoom through. Now we did all this in the U.S. We refined our stuff, and then then we're like, okay, we're going to put it in someplace different, like Botswana, and kind of test if some of the things that we're thinking about, one, holds up in a new place where the cultural norms are different, but is it feasible, is it usable for this affordable robot to be used in this setting? So most of you may know that Botswana is in the southern half of the African continent, just above South Africa. We were working with a variety of of kind of entities there, the University of Botswana, Faculty of Medicine and Engineering, and this was funded through NIH and a couple of, and the Fulbright, the US State Department, to do this work. Botswana, fourth highest prevalence of HIV, 2 occupational therapists, that means dealing with the upper limb, only 2 in a 533-bed hospital, that means nobody was getting therapy. A third of the stroke survivors had HIV. So this is, we toured lots of the centers that they're doing therapy. People were being sent home right after they discharged they came back every month for therapy. We know that that's not sufficient. So again, it was the ideal place to say, can we put our system here, and what is it feasible? Will the therapist accept it? Will the patients accept it? So first goal was to develop the therapy system there in Botswana. This was my student. First, we brought the robots with us. And then we commissioned our Faculty of Engineering colleagues to build a platform there, which was a lot cheaper. And then we basically then mounted the robots on the platform. And we tried to be kind of sensitive to what kind of materials we could get there and things like that. Anecdote is that we thought, 3D printing, that's the way to go. They had a 3D printer. To get something 3D printed took forever, and then they were very careful with the spools because the spools were imported. They were 4 times the cost of the spools in America. So dealing with those types of issues, and so ironically they switched to wood for the cover because it was just cheaper to get the wood. And so it made me think about 3D printing and the assumptions that we make. But anyway, so we now have 2 systems. One that's set up. We ended up, because of COVID, having 2 robots as opposed to 3 because of kind of getting people away from each other. So there are 2 robot systems here. We have one in Gaborone and then one in a hospital. We were able to put one in the occupational therapy department in the hospital. And so right now we're running studies where we're using the robots to assess, and now we're actually in the phase where we're trying to do therapy. In the feasibility study, just quickly, the first part was we collected patients HIV, stroke, and stroke, and then the second part was to do therapy with them. This was the Botswana population. Age-wise, a little bit, about the same as our U.S. population, but a little bit younger in the HIV and stroke. Remember, I said that the HIV and stroke population appeared to be younger than the one in the U.S. Lot less education in the HIV in terms of over age of 12. More moderate on average in terms of their functioning, and definitely more. They had more motor function than the U.S. group as well. We expanded the clinical assessments to include some mobility ones as well as some verbal fluency type testing. We did the 3 motor tasks, the same setup and this was then now done in Botswana. We did the NBAC as well as the spatial span task. Then we actually asked usability surveys. So we had 3 standard ones that you usually use in robotics. The NASA TLX, if you guys are familiar with that for task demand, how this was the usability scale. And then the self-assessment mannequin, talking about how excited you were, how enjoyable. Just quickly. This is kind of when we plot the box and block. So what I did was I just plotted for you quickly the box and block score with the Z-scores and the MoCA score. This line is our moderate functioning line. This line is our severe functioning line. And this is mild to normal, severe to moderate. Notice how many people are falling below that line. And this is where we normally treat. Right? And so it's always surprising for me to see how many people are below where we normally treat, right? And so in the HIV only, HIV and stroke, and then the stroke population. So it suggests that we're able to stratify just even with clinical scores, but if you don't have clinical scores, can you do the same here? So just, this is actually new data, so we're still in the process of analyzing, but there was a colleague who had went to Botswana before and worked with the HIV population, and these were N equals 30 was the number of people she had looked at in terms of who was impaired, and she did similar tests. The cohort in the US, when looked at that, they had less impairment. The cohort in Botswana, you see that the impairments are higher. And this is actually, for me, interesting because now this is the cohort that we're just now going to get into the robotic stuff and how much insight we can gain from that population. Was it feasible? I think in general, lower is better in this particular engagement, the self-assessed mannequin. Most people enjoyed the encounter. They were relatively excited by it, and they felt in control. So at the end of the day, there was some difference across the HIV stroke and the people with HIV and stroke population. The lower numbers really says, hey, for the most part, the people with HIV enjoyed it. The people with stroke had mixed reviews. I actually thought it was going to be the opposite. But what I really think was happening is the people with HIV are normally ignored. And so in some sense that they were excited to just have people listening to them. I'm going to go quickly. Mental demand, physical. People were, in terms of the different population and the therapists, people were feeling that it was reasonable. It was somewhat demanding, but it was reasonable. And so for most part, people weren't really that frustrated with it. You see that the stroke survivors were a little bit more frustrated because they were a little bit lower in function. And so it was harder. But this is kind of how overall task demand, we see that it was kind of in the 50-60. And the stroke survivors felt that it was much more challenging. System usability scale, most people thought it was usable. 68 is kind of like the cutoff. They said we again have, and this I think we need to explore, is like why the stroke survivors are less challenged, with our system. But we see that the system was quite usable and that people were feeling like this is actually a reasonable thing for us to bring to Botswana. So I actually thought this was good results. I'm just going to quickly wrap up here and just say we haven't dug as deeply as we did with the US cohort into all the nuances in the motor data, and that's actually our next phase. We just finished collecting a lot of this data, and in part 2, we're starting to do now the therapy. So bottom line is we're doing the therapy part, and we're starting to deploy the games, and our goal is to collect data on the therapy. I know I'm running out of time, so I'm like, the challenges and opportunity, rehab's complex, so it is important to look at motor and cog in looking at kind of how do we recover function and sustain it. I think the key thing is the idea of being able to create affordable systems that can be effective as assessment and therapy tools. I think we're beginning to provide some evidence of that. And I think in the global space, I think robots can work in that space if we get them to be manageable. I'm not saying that these are very expensive systems are not in low and middle income countries. They are, but they're in very specialty places, and the average person does not have access to them. So that's kind of like me, us trying to push this. And it's the same thing in the US, the average person may not have access still to the robotics. So some takeaways in terms of affordable therapy. If you're going to be in Botswana and places like that, I would say, we really need to think about partnering with the local engineers as well as clinicians there in order for these things to work, really. And I think my biggest lesson is how the difference in the dollar and how that makes such a huge difference. And all the things I'm like, oh, it's affordable. And they're like, no, it's not. And so that was actually just eye-opening. And I realized that it's not as simple as even I was making it out to be, right? And that there needs to be just stronger collaboration if we're going to make this happen. So I'm going to just stop there. And my guidelines, if anyone want to work in this space, affordable, multi-purpose, they still need to be effective, needs to be community-based and appropriate, and we have to build capacity. Without the rehab medicine doc, what I'm doing doesn't work. Without engineers that know are associated with rehab, most of the engineers there are not even thinking about medicine, and if they are, they're considered technicians. They just get in the hospital and they're fixing things, but they're not innovating. They're not thinking through how to build new things. And a part of what I've been doing where the Fulbright was to educate, to try to train the next generation of engineers to be able to apply their skills within this field. So rehab capacity building is important. All right, these are all the folks that funded us, and I thank you. I'm sorry for going over. I went over quite a lot, so I apologize for that. But thank you for bearing with me. Take care.
Well, thank you for a very inspiring talk. And so I'm going to ask a question from the online audience first, but anyone here who has a question, Kai will pass around a microphone. So you can
Should I put back on my mask?
Let's see. And so this question is from Eileen. She says, this is with reference to the motor cognitive portion of the talk. As far as cognitive function or tests, is your team primarily looking at memory function, or are there other cognitions besides memory tested for?
A good question. So if you saw the diversity of clinical tools that we were looking at, we were digital symbol coding is information processing. We did the general MoCA, the Montreal Cognitive, that looked at a variety of different domains, but it didn't delve deeply into any domain, but gave us insight. In Botswana, we added language. We added verbal fluency as a part of the domain. The color trails 1 and 2 are looking at visual spatial functioning and then executive functioning. So we are actually looking at what the different domains are, and as well as working memory, and trying to figure out how each of those domains relate to our task. What we found out quickly was in the robotic tasks that we were doing, it seemed like executive function and working memory and information processing were most sensitive to what we are doing. So those then became kind of like the domains that I think we're kind of going to delve in much deeper.
Great, thank you. Let's see. I have a question, but I actually am sensitive to the time, so maybe I'll ask you during our one-on-one. And if anyone does have questions, please feel free to just come to the podium afterwards. I think that we'll just thank our speaker now.